In this video, we will explain how quantum Fourier transform works and why it can be useful in a quantum computer and in quantum algorithms. The quantum Fourier transform, also known as QFT, like the classical Fourier transform, takes the data from the original signal representation to the frequency domain representation. The difference between them is that the quantum one operates in a superposition state, and thus produces a different superposition state as the output. Quantum Fourier transform is based on using interference as the components of the superposition, which can interfere either constructively or destructively, depending on their amplitude and phase. First, we shall develop the math behind the quantum Fourier transform. We can say that the quantum Fourier transform applies as a unitary gate U QFT. Then, for a general state of n qubits, it is applied in such a way that we are left with a superposition of states psi in of the same weight with different phases. Earlier, we said that the quantum Fourier transform can be seen as a unitary gate. This is done by showing that the QFT can be decomposed as a product of unitary gates, which consist of Hadamard gates, rotations of different angles, and swap gates. Importantly, a product of unitary gates is a unitary gate. For example, let's examine what happens in a 2-qubit system. This QFT has the following circuit representation. Adding more qubits involves the product of more and more of such unitary gates. Now we want to observe the effect of the QFT. To do so, we will show an example using a 2-qubit system. We can write the possible states using a 2-qubit system in 3 ways. With the bracket notation, we can either use decimal or binary, and we can also use vector representation. First, we will apply QFT on the 0-1 state. Following the formula that we have presented previously, we get the following result. Alternatively, we can represent the QFT on the state as the phase rotations to the qubit. The QFT gives a different phase to each state. The pattern goes as follows. The qubits in the first position starts put. In the second position, we rotate the qubits a quarter, generally 1 over n, where n is the total amount of positions our qubits can be in. In the third position, we rotate by 2 over 4 or half. Finally, in the last position, we rotate by 3 over 4, or minus 1 over 4. We will now apply the QFT to all of the states in our 2-qubit system. We get the following results, which together represent the quantum Fourier transform. Let's say we want to apply the QFT to a superposition of states in our example. Note that applying QFT to a superposition is the same as applying QFT to each of the states in the superposition and then adding the different QFTs. In this way, we see that the different QFTs always either destructively or constructively interfere. Importantly, the points where we get constructive interference come at a certain frequency f. Remember, this is a Fourier transform. We move into the frequency space here. In the example, we see that we get destructive interference in the second and fourth position, and we get constructive interference in the first and third position. After this, summing all the QFT outputs of the initial superposition, we see that the constructive interference occurs with a frequency f. Where do we go from here? Let us take Shor's algorithm as an example. Now that we have our frequency, we must realize that the period we are searching for in Shor's algorithms is p equals 1 over f. Now that we have our period, we are one step closer to solving for our prime factor. In general, we can see that this tool can be useful for many algorithms in quantum computers. As we've seen, Shor's algorithm is based on period finding, which is exactly what Q of t does. We hope this video elucidates the quantum Fourier transform and can thus help you better understand how and when to use it.